rotational inertia of a rod about the end. So let's say we have a rod, this long thin rod here. It has a length L, it has a mass M, and it has a pivot point here on the end of it. The linear mass density is uniform, so all little pieces of mass have the same ratio of mass to length. If we look at a little bit of mass here, this little dm, and it has a width here of dx, okay, and it is a distance from the pivot point that I'm going to call x, then we can write the integration of r squared dm as the rotational inertia, where r will be x, that's the distance from the pivot point. And if lambda is equal to the mass per length, then it would also be equal to dm over dx, which means that dm is equal to lambda dx. So now we can make a substitution of dm back over here, and r will be x. So then the rotational inertia of the rod about the end would be the integral of x squared times lambda dx. And then we're going to integrate from 0 to L. We're going to integrate from the pivot point to the very end, summing up all the mass. And so lambda is constant, and we'll integrate from 0 to L of x squared dx. And then this would be equal to lambda times x cubed over 3 evaluated from 0 to L, which would be lambda L cubed over 3 minus 0. Now, if lambda is the ratio of mass to length, and it's the whole mass or the whole length of our rod, then we can substitute this in for our lambda there, and we'll have that the rotational inertia is equal to our mass per length times L cubed over 3. And you see that an L here and an L there cancel out, and that leaves us with a rotational inertia of mL squared over 3. And you'll see dimensionally that this is kilogram times meter squared, so it matches our expected relationship. So now we can use this as the rotational inertia of the rod about its end is 1/3 mL squared. Now let's find the rotational inertia of the rod about the center. It still has a mass m and a length L, and the mass per length is still uniform, so that ratio is the same for every point. But now we're starting from the center here, where this will be 0, and this point over here will be negative L over 2, and this point over here will be L over 2 to get the L distance between the two. So then if I evaluate a little chunk of this rod, it is a distance x from the center, and it has a mass of dm and a tiny little width of dx. So we're going to sum up all those little bits of mass to determine the rotational inertia. So I is equal to the integral of r squared dm. So again, r is equal to x, and lambda is equal to the ratio of dm to dx, which means that dm is equal to lambda dx, just as we did earlier. So now when we substitute in, we'll integrate x squared lambda dx, but our boundaries will be negative L over 2 to L over 2 for our rotational inertia. So we will integrate this and have x cubed over 3 lambda from negative L over 2 to positive L over 2. So bringing the lambda out in front, and we can go ahead and substitute in that lambda is mass per length. times, we'll have L over 2 all cubed over 3 minus negative L over 2 cubed over 3. So then we can say that mass divided by 3L, I brought that out, and then I'll have L cubed over 8 plus L cubed over 8. So that gives me 2L cubed over 8 inside the parentheses. This will simplify to 1/12 ml squared, because our L's will cancel 1 and 1, and 2 and 8 will make 4, and 3 and 4 make 12. So this is our rotational inertia of a rod about its center. Now let's look at the difference in these two. So about the end, the rotational inertia is ml squared over 3. About the center, we get ml squared over 12. So the difference in these two, 1/3 minus 1/12, is equal to ml squared over 4, which would be equivalent to m times L over 2 all squared. And notice that this L over 2 is the distance from the center of the rod to the end of the rod. That would be D. So we can write a general equation for the rotational inertia of any object about a new pivot point as being the rotational inertia about the center plus md squared. This is called the parallel axis theorem. So a hoop having a mass of m, and that hoop has a rotational inertia of mr squared about the center. If we move it to another position where we let it pivot about a point up here, that distance would be r. So the rotational inertia using the parallel axis theorem will be mr squared plus the mass of our hoop times the distance it's offset, which in this case would be equal to r squared. And we get 2 mr squared.